Hello, and welcome. Today we'll be exploring the intersection of flow chemistry and polymerizations, a powerful combination that is transforming how we think about creating macromolecules. This work, presented by Professor Rigoberto C. Advincula, takes us from fundamental principles to advanced applications. When we think of polymer production, we often envision large-scale industrial facilities, like the Bayport Polymers plant. This is the world of polymer reaction engineering, where the goal is to efficiently and safely produce polymers with specific desired properties. Traditionally, this has been done using large batch reactors. However, a newer paradigm is emerging, centered on the technologies of microfluidics and microreactors.
Let's compare the traditional approach with this new technology. On one hand, we have conventional batch technology, where reactants are mixed together in a large vessel and allowed to react over time. On the other hand, we have what is described as a superior continuous flow method using a microreactor. This new method offers several distinct advantages. It provides overwhelming energy efficiency, dramatically reduces the lead time for production startup, and leads to a dramatic reduction in byproducts. This also means energy conservation is attained, and the entire process is inherently safer. The fundamental difference in process is also key. A batch-type process is a single contained event. In contrast, the continuous flow method involves a sequence of precise operations. First, two or more streams are brought together for mixing. Second, they flow through a channel or tube where the reaction occurs. And third, the product stream can be divided or collected continuously. At the heart of these flow systems are micromixers, which are critical for ensuring that reactants combine effectively. They can be broadly categorized into two types: passive and active micromixers. Passive micromixers rely on the geometry of the channel to induce mixing. Examples include simple T and Y-shaped junctions where fluid streams meet, sequential lamination micromixers which split and recombine fluids to increase the interfacial area, focusing enhanced mixers, and droplet micromixers, which use discrete droplets to compartmentalize reactions. Active micromixers, on the other hand, use an external energy source to stir the fluids. This can be achieved through a pulsating pressure field, electrokinetic forces, dielectrophoresis, which uses non-uniform electric fields, or even ultrasound, which uses high-frequency sound waves to create cavitation and turbulence. A simple visual can help us understand this. In a microchannel, flow is often laminar, meaning fluid streams flow parallel to each other with very little mixing. By introducing an active element, like an oscillator creating vibrations, we can disrupt this laminar flow, creating a mixing zone where the flow becomes turbulent, leading to rapid and efficient mixing.
Beyond the design of the mixer itself, other conditions like the flow rate can also profoundly influence the mixing status.
Let's consider an example of a T or Y-shaped mixer. At a very low flow rate, characterized by a low Reynolds number, say around 12, we observe what is called stratified flow. The two fluid streams simply flow alongside each other with minimal mixing. As we increase the flow rate to a Reynolds number of about 80, we start to see the formation of vortices. This vortex flow begins to fold the fluid streams into one another. If we increase the flow rate even further to a Reynolds number of 240, we achieve what is known as engulfment flow, where one fluid stream aggressively wraps around and engulfs the other. The key takeaway here is that the swirling of the fluid flow, obtained at higher Reynolds numbers, results in better dispersion of the fluid within the channel volume, and therefore a significant improvement in mixing quality. This level of control gives flow reactors a distinct edge over their batch counterparts for material synthesis. A typical batch reactor is a stirred tank where reactants are combined. In a flow reactor, reactant streams are continuously fed, mixed, and reacted. This continuous approach offers superior control over a wide range of reaction conditions. For instance, flow reactors provide for very fast mixing and allow for very short residence times, meaning the time the molecules spend in the reactive zone can be precisely controlled. The reaction temperature is also well defined, and because of the high surface area to volume ratio of the small channels, thermal transfer efficiency is extremely high. This makes it easy to manage heat, especially for highly exothermic or endothermic reactions. It's also straightforward to control pressure. Some commercial systems can operate up to 200 bar. Furthermore, for reactions involving solid catalysts or reagents, there is no need for a separate filtration step, as these can be packed into a column through which the fluid flows. This design also makes it very convenient to perform multi-step reactions by simply connecting reactors in series, and perhaps most importantly for industrial applications, it is often easier to scale up production.
Let's look at some concrete examples in organic synthesis. In one case, an asymmetric transfer hydrogenation was performed in a flow mode. The system achieved a 95% conversion with a 90% enantiomeric excess, and crucially, less than 1% of the precious metal catalyst leached out, a significant advantage for both cost and product purity. Another powerful example is a 3-stage synthesis for Bhakti protection. This process was run at a high temperature of 300 degrees Celsius and 100 bar of pressure. Remarkably, this multi-step reaction, involving coupling and deprotection, required no additional reagents, had broad substrate scope, achieved over 99% conversion, and the entire process took less than 10 minutes from start to finish. These examples illustrate several key principles. Well-designed sequential multi-step reactions can be easily approached using a flow system. Various energy sources, such as thermal heating, UV irradiation, or microwaves, can be readily integrated to meet the requirements of different applications. The ability to use high temperatures combined with good thermal transfer leads to very high reaction efficiency. It's easy to apply high pressure, and the system is convenient for heterogeneous reactions, eliminating the need to separate the catalyst after the reaction is complete.
The efficiency of flow systems is also evident in pericyclic reactions. Here, reactions were carried out in microreactors using inductive heating, where silica-shelled iron oxide nanoparticles were used to absorb energy and heat the surrounding fluid. In 3 different examples shown, the flow reactor consistently provided higher yields compared to the equivalent batch reaction, even when the temperature was kept the same. For instance, in the first reaction, the flow system achieved a 75% yield compared to only 52% in the batch reactor. This trend continues for heterocyclic reactions. A table shows the conversion for a series of 2 aminothiazole syntheses. While in some cases the batch and microreactor conversions are similar, in others the microreactor shows a clear advantage. For the synthesis of an acetyl-bromo-substituted thiazole, the microreactor achieved up to 99% conversion, while the batch synthesis only reached 83%. For some target products in heterocycle formations, the microreactor can clearly lead to higher efficiency.
Another classic organic transformation, the Wittig reaction, also benefits from flow chemistry. A study compared the product yields for 4 different aldehydes using both a microreactor and a traditional batch method. In every single case investigated, methyl 4-formyl benzoate, 3-benzoyloxybenzaldehyde, 2-naphthalaldehyde, and 5-nitrothiophene 2-carboxylaldehyde, the microreactor produced a higher yield than the batch process. Flow systems also excel in redox reactions. A multi-step process involving a polymer rearrangement was studied in both a microscale flow system and a macroscale batch system using various alcohols. The results were compiled in a detailed table. The conclusion is unambiguous. A higher yield of the desired products and a lower yield of byproducts were obtained when the microscale flow system was utilized. For example, with 1-decanol as the substrate, the flow system produced the desired product in 75% yield, while the batch process yielded only 11%, with the majority of the material remaining as unreacted starting material or side products. This demonstrates superior selectivity and efficiency in the flow system. The benefits are not limited to these specific reaction classes. In a nitration reaction, moving to a flow system increased the yield of the desired mononitrate mixture from 55% to 75%, and just as importantly, increased the product purity from 56% to 78%. In another example, an 89% yield was obtained within just 1.8 minutes, with an impressive throughput of 91 grams per hour. And in a third case, the yield was dramatically boosted from a mere 15% in batch to 83% in the flow reactor. Beyond small molecule synthesis, microfluidic systems are exceptionally well suited for the fabrication of micro and nanoparticles. A common setup is a T-junction microfluidic device, where a dispersed phase is sheared off into droplets by a continuous phase. This technique can be used to prepare highly uniform, or monodisperse, emulsions. For example, one can create double emulsions, water droplets inside oil droplets, which are themselves suspended in water.
A histogram of the particle sizes from such a process shows incredibly narrow distributions. The internal water droplets had an average diameter of 52.2 microns, with a coefficient of variation of only 2.7%. And the external oil droplets had an average diameter of 83.4 microns, with a variation of only 2.8%. This level of control is very difficult to achieve with bulk emulsification methods.
Another powerful technique is the flow focusing device. Here, a central stream of fluid is squeezed by two outer sheath fluid streams, causing the central stream to break up into uniform droplets or particles. What's fascinating is that by simply changing the flow rates, one can produce monodisperse microparticles with a variety of different shapes, from spheres to rods to disks, all from the same device. This control extends down to the nanoscale. For the fabrication of nanoparticles via nanoprecipitation, a solution of a polymer like PLGA-PEG in acetonitrile is rapidly mixed with water, causing the polymer to precipitate out as nanoparticles. When this is done in a flow system, the resulting particles are smaller than those produced by bulk mixing. Furthermore, the particle size can be tuned by adjusting the ratio of the two fluid streams. A lower flow ratio of the polymer solution to the water results in smaller nanoparticles. Studies also show that higher encapsulation efficiency and drug loading can be achieved using flow systems. Flow chemistry is also uniquely capable of handling gas phase reactions safely and efficiently. There are several methods to introduce gas into a liquid stream in a flow system. The tube-in-tube reactor uses a gas-permeable inner tube inside a solid outer tube, allowing gas to diffuse into the liquid. One can also use segmented flow, creating alternating plugs of gas and liquid, which induces internal recirculation within the liquid segments and enhances mass transfer. Other configurations include annular flow, with a central gas core, or a falling film reactor, where a thin liquid film flows down the walls of a tube filled with the reactant gas. Let's consider an example using a toxic gas, like carbon monoxide. The high heat and mass transfer rates of microreactors make the process much safer and more efficient. In the synthesis of alpha-ketoamides via carbonylation, the flow system consistently produced much higher yields compared to a batch reactor. For the substrate iodobenzene, the total yield in flow was up to 55% compared to only 25% in batch. Similarly, homogeneous hydrogenation using a tube-in-tube reactor demonstrates the precise control available. With the help of a back pressure regulator, it's easy to control the system pressure. A hydrogenation reaction was completed in just 93 seconds under 25 bar of pressure. For a whole range of substrates, the conversion reached 100%. Other gas phase reactions involving oxygen, carbon dioxide, ammonia, and ethylene have also been successfully implemented in flow systems, showcasing the versatility of this approach. Now, let's transition from general synthesis to our main topic, polymerization. We can contrast the conventional approach using a round-bottomed flask with a mechanical stirrer with a continuous flow process. In flow, the initiator and monomer solutions are precisely pumped, combined in a micromixer where mixing happens on a very short timescale, and then flowed through a reactor to generate a well-defined polymer. Let's start with free radical polymerization, a common but often difficult to control method. In a study on the polymerization of methyl methacrylate, or MMA, using AIBN as a radical initiator, a microreactor was compared to a macro-scale batch reactor. The most telling result is the polydispersivity index, or PDI, which is a measure of the breadth of the molecular weight distribution. A PDI of 1 indicates all polymer chains are the same length. In the microreactor, the PDI remained consistently low, around 1.8, across various residence times. In the batch reactor, however, the PDI was significantly higher, over 2.1, and more variable. This shows that microreactors are quite effective for molecular weight distribution control, especially for a highly exothermic reaction like free radical polymerization. The superior heat transferability of the microreactor is believed to be responsible for this high level of control. The more exothermic the polymerization, the more effective the microreactor is at managing the reaction and controlling the molecular weight distribution. To gain even greater control over polymer architecture, chemists have developed controlled radical polymerization, or CRP, techniques.
These include atom transfer radical polymerization, or ATRP, which involves a reversible equilibrium between active radical species and dormant species, mediated by a transition metal complex. Another is reversible addition fragmentation chain transfer, or RAFT polymerization, which uses a chain transfer agent to mediate the polymerization. And a third is nitroxide-mediated polymerization, or NMP, which uses a stable nitroxide radical to reversibly cap the growing polymer chains. All these techniques can be powerfully implemented using flow chemistry. For example, ATAP was conducted in a photopolymerized microfluidic device. By varying the pumping rates and initiator concentrations for the polymerization of a monomer called HPMA, the molecular weight could be systematically tuned, as demonstrated by the shifts in the gel permeation chromatography, or GPC, traces.
RAFT polymerization is particularly well suited for creating block copolymers, where distinct blocks of different monomers are joined together. A microfluidic setup can be designed with 2 reactors in series. In the first reactor, the first monomer is polymerized. The resulting homopolymer then flows into a second reactor, where the second monomer is introduced, growing the second block. This can be done using either segmented flow or continuous flow, making it a flexible approach for creating complex polymer architectures.
Flow chemistry also enables polymerizations under extreme conditions. High-temperature cationic living polymerization was conducted at temperatures up to 180 degrees Celsius in a flow system. Even at these high temperatures, the molar mass dispersity could be well controlled at a low level. The high polymerization efficiency made it possible to synthesize complex diblock and triblock copolymers in a very short time, on the order of just 5 to 7 minutes for each block. Anionic ring-opening polymerization has also been demonstrated. In the polymerization of an amino acid N-carboxy anhydride, or NCA, GPC analysis of the resulting polypeptide showed that the molecular weight could be controlled by adjusting the flow rate. Slower flow rates correspond to longer reaction times, which in turn produce higher molecular weight polymers. A key question for any new technology is scalability. Can we make large quantities of material? One approach is called numbering up, where instead of making the reactor larger, multiple microreactors are run in parallel. A study of scaled-up free radical polymerization in a microflow system showed remarkable stability. A graph tracking the molecular weight and PDI over 7 days of continuous operation shows that the polymer properties remained constant, proving that the microflow reactor can keep producing polymer with stable properties for extended periods. This scalability also applies to controlled polymerizations. A scaled-up RAFT polymerization was performed, producing 500 milliliters of polymer solution. When the properties of the polymer made in a small 3 milliliter batch, a large 100 milliliter batch, and the 500 milliliter continuous flow system were compared, the results, conversion, molecular weight, and dispersity, were all very similar. This demonstrates that the excellent control achieved at the microscale can be translated to larger production volumes, and the scaled-up process for the flow reactor is much easier to implement. The Advincular Research Group has utilized this technology extensively, using an automated Phoenix reactor from Thales Nano. This system allows for reactions from 10 to 450 degrees Celsius and pressures from 1 to 300 bar. It can handle up to 13 different reagent gases and is suitable for both heterogeneous and homogeneous catalysis, all within a fully automated system. This instrument takes the principles we've discussed, precise mixing of initiator and monomer, flow through a heated polymerization section, and then a cooling section for termination, and implements them in a robust, versatile platform. Interestingly, this type of reactor is not limited to polymer synthesis. It can also be used for other applications like oil and gas testing, for example, to measure the permeability of core samples under high temperature and pressure conditions, or for rapidly screening chemical formulations for enhanced oil recovery. Let's now dive into a specific case study on highly efficient RAFT polymerization in an ethanol-water mixture. The central hypothesis links the physical advantages of flow systems to chemical outcomes. The high thermal transmission efficiency should lead to a more homogeneous product with a narrower molar mass dispersity. Operating at a higher temperature shortens the half-life of the initiator, which in turn leads to a higher propagation rate and overall higher efficiency.
However, higher temperatures can also increase termination and chain transfer rates, which might lead to a broader molar mass dispersity, so there is a balance to be struck. To understand the kinetics, the half-life of the initiator, ACVA, was calculated at different temperatures using the Arrhenius equation. At 60 degrees Celsius, the half-life is 36 hours, but at 100 degrees Celsius, it drops dramatically to just under 8 minutes, enabling much faster reactions.
Evidence of polymerization was collected using several techniques. FTIR spectroscopy shows the disappearance of the carbon-carbon double bond peak of the monomer after polymerization. The proton NMR spectrum of the raw product confirms the conversion of monomer to polymer.
After purification, the NMR spectrum of the pure polymer is clean, and GPC analysis shows a well-defined polymer with a molecular weight of 28.6 kilodaltons and a low dispersity of 1.12.
A summary of results from various experiments reveals the level of control possible. By varying the molar ratios of monomer to chain transfer agent to initiator, and by adjusting the flow rate, which controls the residence time, the monomer conversion, molecular weight, and dispersity can be systematically tuned. For example, at a fixed residence time of 26.6 minutes, increasing the initiator concentration leads to higher conversion and molecular weight. This systematic data allows for the targeted synthesis of polymers with desired properties.
This work extends to more complex architectures as well, such as the synthesis of hyperbranched polymers via thiol-yine chemistry in a flow reactor, demonstrating the breadth of polymerization techniques amenable to this approach. Let's move to a second very powerful application, the continuous synthesis of polymer brushes grafted from silica microparticles. Polymer brushes are dense layers of polymer chains attached at one end to a surface, and they can dramatically alter the surface's properties. The workflow for creating block copolymer brushes is greatly simplified by flow chemistry. First, the particle surface is modified. Then, the first monomer is added and polymerized from the surface. When a block copolymer is needed, the particles can be easily washed in situ simply by flowing solvent through the reactor. Then, the second monomer is introduced to grow the next block. This avoids the tedious process of removing, washing, and repacking the particles that would be required in a batch process. The process begins with the synthesis of a silane-modified RAFT CTA. This molecule has a RAFT agent on one end and a trimethoxysilane group on the other, which can covalently bond to the surface of silica particles. The experimental setup involves packing these CTA-modified silica microparticles into a column, which then acts as a packed bed reactor. A solution of monomer and initiator is then flowed through this column at a controlled temperature and pressure. The polymerization is initiated in the solution, but the growing chains are controlled by the RAFT agent's anchor to the particle surfaces, resulting in polymer chains growing directly from the particles. To create a block copolymer, a solution of the first monomer, PEGMEMA, is flowed through for 1 hour, followed by a solution of the second monomer, NIPAM, for another hour. The presence of these polymer brushes is confirmed by IR spectroscopy. Spectra show the appearance of characteristic polymer peaks after the grafting reaction.
Thermal gravimetric analysis, or TGA, which measures weight loss as a function of temperature, is used to quantify the amount of grafted polymer. TGA results show that the chain length can be controlled. Longer flow times or higher monomer concentrations both result in a greater weight loss, corresponding to more polymer being grafted onto the surface. GPC traces of the polymer brushes after they have been cleaved from the silica surface confirm these findings. Both longer flow times and higher monomer concentrations lead to higher molecular weight polymers, and a table summarizes this data, showing systematic control over the grafted chain length. For the block copolymer synthesis, FTIR confirms the presence of the second block, PNIPAM, by the appearance of its characteristic amide peaks. TGA also confirms the successful block copolymerization, showing a greater total weight loss compared to the initial homopolymer brush. The most direct evidence comes from GPC, which shows a clear shift to a higher molecular weight after the second block is added. NMR spectra of the cleaved block copolymers further confirm their chemical structure. These surface modifications have a profound impact on the material's properties. The static water contact angle of the surface changes dramatically. Grafting with these polymers can make the surface significantly more hydrophobic. For the block copolymer containing P-NiPAM, a temperature-responsive polymer, the surface properties become switchable. At room temperature, the contact angle is 95 degrees, but when heated to 60 degrees Celsius, the P-NiPAM chains collapse, and the surface becomes even more hydrophobic, with a contact angle of 116 degrees. It's important to note that attempting a similar graft-from reaction in a batch reactor led to a problem. The solution gelled in less than an hour, preventing any further grafting. The superior heat and mass transfer in the flow reactor prevented this unwanted side reaction. A final example involves grafting hyperbranched polymers from surfaces. Using a dual-phase ATRP process in a flow reactor, a solution of monomer and catalyst was flowed through a column packed with initiator-anchored silica particles. This resulted in the successful grafting of hyperbranched PDMAEMA. The functionalized particles were thoroughly characterized by NMR, GPC, FTIR, and TGA. SCM and XPS confirmed the morphology and surface composition. The resulting brushes showed responsive wetting behavior to both pH and temperature. As a demonstration of function, these particles were used for dye absorption. The amount of dye they could absorb was dependent on the pH, showcasing their potential as smart, responsive materials.
In conclusion, we have seen that flow chemistry offers a powerful platform for polymerization. The ability to use high pressure allows for high-temperature reactions, which increases polymerization efficiency. The inherent high thermal transfer efficiency of these systems also leads to higher efficiency as well as more homogeneous products with better defined molecular weights. Finally, the continuous nature of the process makes it possible to graft polymers from microparticle surfaces without additional purification steps, which in turn makes it much easier to fabricate complex architectures like die block copolymers or even sequential block polymers.
Thank you.